All right, recording is started. So for the next couple of lectures, we're going to talk about strings and data structures for strings. And this is a weird one because it's probably about 3 lectures, but they're going to be split by the break. So today, we'll make sure everybody has sort of the same background. For some of you, there'll be some review here. There's not really any way around that. But after the break, we'll get into things that I think should be new to just about everyone. So what's a string? Well, it's a, and for our purposes, finite sequence of symbols over some alphabet. Sigma, well, that's annoying. Now I've said things like symbols and alphabet, which you also don't know what those things are. Alphabet, I'll define that, is a non-empty set. And for our purposes, we're going to use alphabets that are integers. So let's say size of sigma -1. And sometimes, in addition to those integers, there may be an extra special character, which is not an integer. Or if you like, that special character 0 is somehow the special character in the alphabet. Okay. Okay, so a string, I mean, we all sort of know what it is. I mean, if you've done any programming of almost any type, you will have encountered these strings. But something you may or may not have given much thought to is how are these things represented? And we sort of think we all can guess how strings are represented. I mean, you usually think that you can access the individual characters in a string, each one in constant time, which really means the only thing that a string could be using somewhere is an array. So okay. So yeah, I mean, a string is represented using an array. The characters in the sequence just are the individual elements of that array. It's kind of natural. But if you think about this a little bit, well, then you think, well, how do we represent an array? And I mean, that seems obvious. It's just a consecutive sequence of memory locations. But actually, it's not completely obvious because different languages do it different ways. For example, in the C language, an array is just a pointer to its first element. So the array lives off in memory somewhere, but the variable that refers to the array is a pointer to the first element. And actually, in C, you don't even know the length of the array. So that's not true in all languages, and in things built on top of C, certain C++ libraries, for example, there are strings and there are arrays that remember their length as well. In fact, in C, there's not really any safe way to know the length of, to get the length of an array. So this comes through with strings as well. And there's two ways to deal with this. So a C-style string uses an end of string character. So one special letter in this alphabet is reserved so that it's only allowed to appear at the end of a string. So in this picture, that would be this thing ending in that end of string character. Okay. We'll always use $ for that. It comes from regular expression syntax, I guess. So this is what a C string looks like. It is a pointer to a memory location. If you start reading the characters at that memory location consecutively, eventually you will get to one which is the end of string character. That's how you know you're at the end of the string. That's the only way you can know you're at the end of the string. So that's C strings, but there's an alternative, which is, I'll call them P strings. It uses a length field. So for a P string, there's a pointer to the first character, but there's also a length. So it's a two-part structure. One is a pointer, the other one is an integer. It tells you the length of the string. In this case, the length is 1. And with this length, when you're storing the length like this explicitly, then you don't need a special terminator at the end. It doesn't have to be there. In fact, you don't need a special letter in your alphabet that's reserved for only being at the end of the string. You can use all the letters in your alphabet anywhere you want. All right. So two representations, both showing up in different places. C string because it's the default representation in the classic C language. P string because Pascal used to store strings like this. It was the way it did it.
All right, Pat. So Java uses the second version, right?
Java, the string class.
Yeah, the length.
I think it explicitly stores the length and the backing array.
Yeah.
But I think, I'm not positive, but I actually think Java manages to get the worst of both worlds, as we'll see. It has all the disadvantages of C strings and all the disadvantages of P strings.
Okay.
Well, that's not critical. If you need to, you can write your own string class in Java that works better. All right, so well, what are the advantages and disadvantages? Well, P strings have a number of advantages. One of them is if you ask for the length of a P string, that takes constant time. And if you ask for the length of a C string, that takes time that is proportional to the length of the string, because the only thing you can do is start scanning the string until you find this end of string character. That's a small issue, but a bigger issue is substrings. So something you often want to do with a string is to extract a substring between two indices, right? So I might ask for the substring from index 3 up to index . up to index 10, maybe up to and including index 10. And well, how long does that take? For a C string, you can go straight to the index I, and you can copy the string up to index j into a new array. And don't forget to add an extra place at the end of that array to store. So all of this stuff gets copied. An extra place at the end of the array to store the end of string character. So that takes time, which is basically proportional to the string you're making, which is something like j minus I plus 1. For a P string, though, you can actually do much better. For a P string, what do you need? You just create a new pair pointer right to that memory location where the string starts, and the length, which just happens to be j minus I plus 1. Right? So for a C string, you can extract any substring in constant time. Doesn't matter how long it is. Okay? And that's not true for these C strings. Okay? So this is a C string, and this is what you get with a P string. This is C string, this is what you get with a P string. So for a lot of things, we will want, in fact, for almost everything we do, we'll want P strings. The only idea that we'll borrow sometimes from C strings is this end of string character because it's handy. Yes?
In terms of like time it takes to report the link, for example, we say that it's 01.
Mm-hmm.
But what do we need like log size of s bits to store it?
Oh, so we'll, yeah, I've been a bit lazy about defining the model of computation, but in general, we imagine we're working with a computer that can do arithmetic on integers in constant time if the integers are in some reasonable range. And for us, reasonable range means, well, certainly if they are if they're in the range 0 up to n, where n is whatever problem we're looking at, and usually even if they're in the range 0 up to n to some constant, so n squared, n cubed, or whatever. Beyond that, then maybe you have to think about the time it takes to do arithmetic and stuff. But in this case, and sort of the natural, so how, I mean, why n? Well, n because right, we're talking about problems of size n, which means the computer has a memory of size n, which means that it can index at least n memory locations, which in computing terms means the word size should be at least log n. So it can do arithmetic on log n bit integers. When we want to be fussy about that, we'll do like we did in the previous couple of classes and say it's a computer of word size w, and really study that carefully. But it doesn't really make sense to have w smaller than log n, because that means you have a problem which is so big your computer can't even address the whole problem. So yeah. Any advantage for C strings? Well, I mean, there's some really dumb advantage. Like this is only 1 byte. If you're using, let's say, 1 byte characters, this is only 1 byte of memory, whereas this length thing might be 4 bytes. That's not really an issue anymore. But the sort of useful idea is a special character that only appears at the end of the string, or in some cases we'll find, in fact, we've seen this already when we looked at the Burroughs-Wheeler transform. We had a special character that was actually an important part of the algorithm for the transform. And in the the substrings that it studies, it doesn't only appear at the end, but it only appears once inside every inside of every string. So no, C string is not particularly useful, but this idea of a special character, special end of string character is a good idea. And yeah, so someone asked about Java, and I think I checked into this at some point, but the Java substring operation, I believe, is not that clever. It doesn't do this. It creates a new array and copies the string into it.
Yeah, Java does it that way.
Yeah. So yeah, so don't use the Java strings if you need this constant time substring copying. Okay. All right. So that's well, those are data structures. I mean, this is a data structure for storing one string, two different options. For us, we'll use p strings. Now, what makes strings, let's say, different than other things that we've been studying? Well, there's sort of two issues. One issue is that comparing two strings doesn't take constant time. And that's true if you're comparing them and because you want to know which one lexicographically comes before the other one. So you want to really do a less than kind of comparison. Or if you just want to know if they're equal. The only way to verify that two strings S1 and S2 are equal, in the P string case, you get to take a quick shortcut by checking that their lengths are the same. So that will definitely tell you they're not equal if their lengths are not the same. But if their lengths are the same, then all you can do is start comparing the individual characters of S1 and S2 until you finally find some place where the characters differ. Okay. Or you get to the end and the characters are all the same, in which case you realize they're equal. And that first place where they differ will tell you which, by then saying which of those characters comes before the other tells you the ordering of the two strings, or you get to the end and realize they're equal. Okay. So that takes not constant time, but you can't really say anything more than it takes the minimum of the length of S1 and the length of S2 time. This is true both for C strings and P strings. So that's one unfortunate thing about strings. But a positive thing about strings is the characters, so the elements from that alphabet, are integers. So we can use them as indices. Okay. So we've seen that once you start taking data that you're given and using it as indices into arrays, then a lot of problems can be solved faster than if all you can do with that data is compare them. So pluses and minuses. So let's think about the sort of simplest thing we could do, question we could ask about strings, which is a question we've looked at repeatedly. We want to keep a sorted set of strings. So we want to support the operations add a string, remove a string, and let's say, find a string. And by this find operation, I mean the successor operation that we've been talking about. If string S is in the set, great, you find it, determine that it's in the set. If not, you can find the smallest string, which is bigger than S, or the largest string, which is smaller than S. And actually, let's even forget now about add and remove. And just think about how we store a set of strings. Well, we can go back to the sort of first data structures that we've learned. Well, that actually, if you go way back, if you don't care about adding and removing things, you could have a sorted array. Right? So this one points to some string, this one points to some string, this one points to some string. And if these are C strings, that's all you've got. And if they're P strings, you have a parallel array that has the length of each of these strings. All right, so you store your strings in sorted order this way. So S1 is less than S2, is less than S3, is less than S4, and so on. And by less than, I don't mean the length is less than. I mean that when you start comparing their characters one at a time, the first tie is broken with S1's character appearing before S2's character. All right, so then how long does it take for me to search in this set? It's a sorted array, so I can use binary search. So use binary search. And how long does binary search take? Well, binary search does, I mean, you learn this right away. It takes O of log n time, and it does, if you're careful, something like the ceiling of log n plus 1 comparisons. But does it run in O of log n time in this case? Pardon? Yeah. So binary search, when you usually learn it, it's about searching for numbers or something simple where you can compare two things in constant time. That's not true for strings. Comparing two strings can take time, which is proportional to the length of the shorter of the strings. So if you happen to have a set where all of your strings are let's say, at least as long as S, then and you start searching, and for some reason all your strings are quite similar to S for at least the beginning, then this O of log n becomes O of S plus log n, or sorry, times log n. Because log n comparisons, but each one takes O of S time. And that's not even a ridiculous thing to think might happen, because, I mean, just think of big sets of strings. Think of a company like Google. What are the big sets of strings that they might store? Well, they might store a whole bunch of URLs. What do URLs look like? Well, most of them start with https://. A large number of them then continue on with a very small number of different domain names. And so actually, the huge chunks of those strings, and in fact, the beginnings of those strings, will be a perfect match for the string you're searching for. Okay. So it's not crazy to think that this occurs in practice. All right, so can we beat that? And what could we even hope to do better? So I think we can buy the fact that we're not going to be able to find any string faster than its length, right? To search for something, we have to at least look at the whole thing, right? In particular, just to verify, because if we search for it, that means there's a possibility it's in the set. So just to verify that it's equal to something in the set, you have to read the whole thing. Otherwise, you have no chance of knowing that. Okay, so this looks like it's required. This log n, no reason to think that it's required. But if we're going to do something like this, like a binary search of some kind, where we're always going to take the string we're searching for and compare it to something that's in our set, then, well, those are only sort of binary decisions that happen. We'll also need a log n for comparison. So this one is definitely needed. This one will be needed for a comparison-based structure. Now, nothing says that we have to only do comparisons. In fact, I already foreshadowed that by saying that it's important that the alphabet is integers. We'll make use of that shortly, but let's stick to a comparison-based thing for now. So this is needed and this is needed, but there's nothing that says we have to multiply these two things. Okay. So can we come up with an easy way to, instead of getting s times log n, to get s plus log n? So this sort of target running time maybe gives us an idea about even how the algorithm should look. So it says that, you know, if you think about this in terms of a search algorithm, it says something like, we should either be able to, we should look at a character of s, and then one of two things should happen. Either the size of the set that we're searching in goes down by a factor of 2. And if that keeps happening, that will lead to a log n running time. Or if that doesn't happen, then the character that we look at in S, we hopefully never have to look at it again. So we're done looking at that character. We move on to another character of S. And if we can always do one of those two things, then either we're making progress on S, we're peeling a character off of S, or the size of the set we're searching in is going down. And so that'll lead to this running time. All right, and if we're going to do this, it seems kind of natural to think that maybe what we should be looking at first is the first character of S. Okay, so we're going to look at the first character of S, and we're going to compare it to the first character of some string in our set. We'll call that string M, or we'll call that character M. And we compare that to S at 0. And one of three things can happen. The first character in our string comes before M. The first character in our string is equal to M, or the first character in our string comes after M. So first character is A to L, first character is M, or the first character is N to Z. Now, we would like to set things up so that in each of these three cases, something good happens. Either this total size of the set goes down by a factor of 2, or we never have to look at a character again. We never have to look at the first character again. All right, so what should we put here? So think of this, we're building a binary, we're building a tree here, a search tree. What should we put in the middle here? So we have this big set S. Pardon?
Look for the second character.
Yeah. So down here, we should have something, a tree like this one, but it's going to store all the strings that start with M. Or more precisely, it's going to store the suffixes, the strings that you get by taking each of those ones that starts with M and peeling off deleting M. There's no need to keep deleting M because all of them start with M. And so once you're searching in here, you know that everything in here starts with an M. And then, well, down here, and I'll say minus the first character. Over here, well, we kind of know what we have to store over here. It has to be all the strings that start with the letters that come before M. So with A up to L. And then over here, it's all the strings that start with characters N up to Z. So if I get lucky, the string I'm searching for starts with an M, and then I get to search in here for a string which is one character shorter. So I forget about that first letter M. I never have to look at it again. Otherwise, I have to go here or here. And well, if I pick the character M appropriately, then I can make each of these two sets have at most half the strings in it, right? Just sort all of your strings and put them in sorted order. Take the one in the middle. That starts with some character. We'll call that character M. Then place all of those things down here. And you know then that all the strings that start with A to N, that's at most half of them because they all come before the middle. And this is also at most half of them because they all come after the middle.
Pat?
Yeah.
I have a question. The letters or like the strings that follow M, for example,
Yep.
are those stored as alphabetically or are they like based on some priority that's given?
You're just going to store a, I mean, you're not even going to store them explicitly anymore because they'll show up as paths in this tree. So just let me give an example. Let's say this is the set of strings that I want to store. I have to pick the character that's going to go at the root of my tree. So this is 5 strings. The one right in the middle is map in sorted order. So what's going to go at the root of my tree is going to be an M. There's going to be there's other things that go in there. So app and ake now have to go into here. On this side, I'm going to have to put aardvark and ape. And on this side is going to go zebra. If we look at what that looks like, well, now down here, we only have two strings, app and ake. It doesn't matter which one we pretend is the middle. They both start with A. So we're going to get an A here. Nothing exciting happens there because both of them start with A. So then we have to store the string that is just P and the string that is just KE. We have to choose one to be the middle. Let's say P is going to be the middle. And K comes before P. So it's going to go off to the left. And then we end up with a E here. And up on this side, we're going to have, well, we get to pick whether we use A or P because there's only two strings. Oh, no. No, that's not true. We have to use A here because all the strings start with A. And then from there, we have to pick one of them. So let's take A again. And that means that 8 is going to go over here. And aardvark is going to go over here. And then finally on this side, we have zebra, which is, there's only one string the whole way down. Okay. And now actually we see that we should be a little bit careful if we want to do this right. So if you look at this tree, you say, okay, what strings are stored in here? So certainly if I search for any of these, then I'll be able to find the path that leads to the end, well, that leads somewhere. But you want to distinguish between strings that are stored there and prefixes of strings that are stored there. So the best thing to do is to put these $ on the end, because then you will get from map, you'll get that $ showing up. So it will show up, $ come before everything else. So you get something like this. And same at the end of all these things. Yep. K should not be a child of P. A. No, no, because we were storing strings that start with M, that's these two. Of those, the strings that continue with A, that's both of them again. Then we have to decide what we're going to treat as the median of this two-element set. We have to pick P or K. No. No, A is going to have A is going to have only one child. It's because all of the strings that we're currently considering all start with A. So
sorry, how do you get make without passing P?
how do you get where?
How do you get make without visiting P? So you have.
Okay, so if I go searching for map, then I see M matches this. A matches, go down the middle, which means you forget about M. A matches this, go down the middle, which means you forget about A. P matches this, oh, you're right. So this one should be here. That makes more sense. P matches this, so you go down the middle, and then finally the dollar matches. Okay, that makes more sense. So the dollars always, yeah, they'll always end up being, yeah, they should always end up being middle children.
And so how about make?
Make?
Yeah.
M, A, K is smaller than P, so you go left. And then, well, K is equal to K, so you go down and down.
Thank
Right?
you.
So remember, at each step, you either, if you go down, you forget about the letter you're looking at. If you go left or right, you still remember the letter. So if I'm doing make, I'm getting M, that's a match. A, that's a match. K, that's not a match. Check K again, that is a match. Then E, then dollar. So the letter K gets compared twice.
Thank you.
Pat,
Yeah.
could you clarify in this scenario, how come P only had, so in this case, A had one child, but in the on the left subtree, the A had two children, the bottom A.
Yeah. So in the left subtree, we so the here, so they both start with A. That's where this comes from, but at that point, we're storing these two strings. The aardvark with a single A and PE. Okay, so we have to pick one of those two strings to be the root of our tree, and yeah. So I should. This is a bad picture. So we have to pick one of these two characters to be the root of our tree. It's either A or P. So for whatever reason, we decide to pick A because they're both equally good. Now we have a string where that matches. So that should look like this, coming down as the middle child. And then we have a string that starts with P, which is bigger than A. So that's off to the right child. So
Okay, yeah, that was where the confusion was. I thought it was a left child. So
yeah,
I was
no. This is what happens when you do off-the-cuff examples. Yeah, so this has no left child, has a middle child for all the strings that start with A, and a right child for the other strings, the strings that start with something bigger than A. Okay, and now, you know, when you do this, you get, well, you get search time that is the length of the string you're searching for plus log n. And that's just because at each step, either the total number, so you can think of it, now when I store a set like this, what I will get is for every string that's in my set, I will have a leaf in this tree that has a $sign, that's a $sign. So all the leaves end up being $signs. So the number of leaves in this tree is the number of elements in the set. And when I do a search, then, or when I take a step in my search, either the number of leaves goes down by a factor of 2, or the one character in my string I'll never have to look at again. So that's where you get this running time. All right. And well, if you want to also support adding and removing, well, now you see that this is kind of like a problem on, I mean, this isn't a binary search tree. It's called a ternary tree, but not a ternary search tree. It's a special ternary trie, I think they like to call it. Then you get an issue of you build one of these things, but you have to do some rebalancing at some point. So you want to keep this thing so that whenever you go left or right, a constant fraction of the leaves go away. There's lots of ways to do that. You can think about how to achieve that using heaps. You can think about how to achieve that using partial rebuilding, which is a common strategy, or even doing something like rotations in these things. So you can there's lots of solutions to make these things so that they stay balanced. But I don't want to talk too much about those. Okay. So those will, this you can achieve all of these operations, adding, removing, and searching in time that's just proportional to the length of the thing you're adding, removing, or searching for, plus log n. Yeah.
So this is the famous phone book data structure.
The famous what?
Phone book, like you're searching the phone book, basically. You heard about the
Yeah. So this is like the phone book, or it's actually like the dictionaries with the holes in the side of them. Not exactly, but right, there's these dictionaries with holes cut in the sides of them, and the hole indicates all the letters that start with some, or sorry, all the strings that start with some letter. So that it kind of gives you the first step of this thing. So using that cut in the side of the page, you can take this thing and split it into two. All the strings that start with something before that letter, all the strings that start with something after that letter, and then this stack in the middle, that's all the strings that start with that letter. But then it doesn't go any deeper than that. It only works for the first letter.
Pat?
Yeah.
Is there a way to improve the efficiency of finding words by being more selective about what ends up being the middle child instead of selecting them at random?
If you're doing comparisons like this, then the absolute best thing you can do is to take the middle child to be the one that, to take the middle character to be the one that defines the median in your sorted set. Then you'll get at most half on each side. So you can't really do much better than that. But we'll see that actually, if you drop this idea of doing comparisons and use the fact that these things are integers, then you can make the log n go away entirely. Okay, so that's one structure. Call that the ternary trie. And all the operations in s plus log n time. The other structure, the next structure is just the trie, and it's one you've seen before. We've seen this so-called binary trie, which was used for storing integers represented as a binary sequence. So they were binary strings over a two-letter alphabet. But there's no reason you can't do that over a larger alphabet. So that's when you get a trie, and it's a tree, but each node in the tree has an array whose length is the length of the alphabet. And basically, it totally avoids ever going left or right. And at each step, it always matches a character of the string you're searching for. So for example, this thing will have a child for all of the strings that start with an A. They'll go down here. So a nice way to think of that is it has an edge coming out of it labeled A. It has another edge coming out of it labeled B, assuming there are some strings in your set that start with B, another one labeled C, and so on, until all the way to the end, and even one at the end, although probably should go at the beginning, that has all the strings that start with the end of string character. And there could be one of those because the empty string, the string of length 0, starts with the end of string character. So that's even possible. All right. So then you get a structure that looks like this. There is a node that corresponds to the first character. And if I look at my set of strings that I'm going to store here, the first characters are A, C, F, and Z. So there's edges coming out of that node with the labels A, C, F, and Z. And although it's not pictured here, there is an array in here of length 26, the number of characters in the alphabet, and A is this edge is a pointer stored in the first element of that array. This one is in the third element of that array. This one is in the last element of that array. And now you continue. So of all the strings that start with A, they have to go over here. Those all start with P. So from this node, there's only one child coming out. And of all the strings that start with P, next one starts with, there's one that starts with an E and another one that has a P. So this has a E, this has a P. And let's not forget, I told you that this would be a useful thing, this end of string character. It's really critical here. So this one has one of those. Apple, we still have to keep going. This is a real simple one. And you get the idea. So that's what the try looks like for this set of strings. And searching is really easy and fast. You have the string that you're looking for. Maybe the string you're looking for is I don't know, something like check. You start at the root, look at the first character. There is an edge coming out of here with that first character labeled by that first character. So there are strings that start with that first character. Look in the subtree that contains all of those, all of the suffixes of those strings. There is then a match for H. There's also a match for E, but at this point, coming out of this node, there is no edge labeled with a C. So you conclude that it's not there. And if you wanted to know what the next string is that was there, you'd be looking in this node now. There's this index C, which is empty. There's this index D, which is also empty. But at the index E, there's a child. And if I follow that pointer down and then always go left, I'll find the smallest thing, which is bigger than what I'm looking for, check. In this case, it's really easy. I follow this down and there's really only one way to go. Okay. Okay, good. All right, so that's just a try. And it can do searching in O of S time. So you can find the thing you're looking for in O of S time. And if you find it, great. If you don't find it, then it depends on what you want out of it. Like if you want the string that comes next in sorted order, then you'll have to pay possibly the length of the answer, not just the length of the thing that you're searching for. Just like we did with check here. At this point, we realize we're not going to find check, so we go searching for the next biggest thing. Yep. You can do all kinds of things here. And depending on how much effort you want to put into that, it kind of depends on how big your alphabet is, whether that's worthwhile. But just one thing to keep in mind is for a really big alphabet, the thing that you usually want to do here is the successor search over a set of integers, which we've looked at. So you can do it fast, not everything in constant time, but you can use some really fancy structures here if you want. Typically, though, you don't do anything special. Well, typically you don't use a try like this, and we'll see why shortly. Okay, good. So that's how long it takes to search. Now, the issue with a try, well, starts to show up when you look at the size. How big is this thing? Well, there's a lot of nodes, and each node is a big array that's as big as the alphabet. So whatever the size is, the size of the alphabet is going to come in there. And actually, if you think about it a little bit more, you realize that if you have a big set of strings, very quickly they can all sort of diverge. And then what you get is this ugly looking thing that's maybe that all the strings share some nodes up here, but then it's just long tails hanging off here. And so when that happens, then essentially you have almost a single node for every character in every string that's in your set. So that looks like something like the size of your alphabet times the sum over all the strings of the length of that string. Okay. This is awkward to write, so let's make a notation for it. We'll call this capital N. And now we'll remember that we have n strings in our set, little n. And capital N is the total length of all strings. So this is kind of prohibitive in terms of space, right? A big array for every character and every string, that gets to be a bit much. But the nice thing about this is, while the other operations of adding and removing are fairly easy, right? So for instance, well, I mean, to add something, you just search for it until the search falls out of the tree. Like if I wanted to add check, I start searching for it, C, H, E. Now I try to follow C, but it's not there. So then I just make the path the rest of the way. That's how you add it. Okay. And well, similarly, when you want to remove something, you find it, which means you find a leaf that has a $, end of string character on it. that indicates it's there. And then you just start erasing the leaf. And then if its parent has no more children, you erase that. And if its parent has no more children, then you erase that. And you stop when you get to a parent that still has a child left. So you get up to a branching node. All right. And well, so that says we can do these operations, but these other operations, add and remove, and certainly add, we have it's not the same speed as searching, because basically we reach a point where we now have to create a new node for each character in the string we're adding. So that is something like the size of our alphabet times the size of the string we're adding. And that kind of had to happen because if we add a whole bunch of strings, we eventually end up with something of this size, which is the total length of all strings. And remove depends how you want to count it. Depends how much you would like to say it costs to remove an array of that size. Is that constant time or is it proportional to the length of the array? It doesn't really matter much. Okay. All right. Good. So the problem there is it's not very space efficient. So let's think about something more space efficient.
Sorry, Pat, when you say size, that's also the time to build it, right?
The size, yes. So if you just build it by repeated insertions, then the time it will take is basically proportional to the size, right? So if you just look at the running time for adding, it's the length of the string times the size of the alphabet. I mean, unless you happen to be adding something that's already almost there. And so, by the end of that, you get something whose size is the total length of all strings times the size of the alphabet. So, okay. All right, so let's try and make this a little bit more efficient. So let's go similar idea. And so before, what we were doing was we were making a tree. We were putting labels on the edges. Each edge was labeled with a character. And then every string is just a path in our tree. Well, we could be a little bit more efficient, maybe. So we'll still do the same thing where you can have as many edges coming out of a node as there are letters in the alphabet, but the labels on those edges can be a bit longer. So in fact, the labels can just be strings. So here we have some strings that start with A, but then they start to differ immediately. So we'll have one of these things with a child, an edge labeled A. And then we have some other stuff. Well, we have one other string left. It starts with a C. We only have one string that starts with a C, or another way to think of it is every string that starts with a C is the same. So we might as well put the whole string on the label on there. So we get one child whose label, whose one edge coming out, whose label is cheese, the other one whose label is A. Now, for second letters of these A things, we have a C, a G, and a P. C, a G, and a P. Well, for the C's, we only have one thing, so we might as well put the whole label there. Same thing with the G. And then for the P, we have two of them and they differ immediately. So we're going to not get away with any more than that. But then it finishes with E dollar and P L E dollar. Okay. Same idea. Same idea as a trie. Every string we have is represented by a path from the root to a leaf. The way you get the string is you concatenate all the labels along that path. That tells you what the string is that's represented there. But now something interesting happens. And well, the interesting thing that happens is we don't have these long dangling things, these long paths hanging here. In fact, if we look at any node which is not a leaf, it has at least two children. If it had only one child, so if it looked like this, well, then there's no reason for that node to exist because there's some label on here and some label on this edge. And if your string, all the strings that you were storing down here, all of them have to begin with that full label. So you could just get rid of this entirely. So except for the root, you don't have any node that has only one child. So everything is either a leaf or it has at least two children. And one of the things you may or may not remember or may not have seen about trees like that is if you have that, then the number of internal nodes is not any more than the number of leaves. So good. So this kind of thing, it's called the Patricia tree. And well, what have we just argued about the Patricia tree? Well, what do we know? N is the number of strings in our set. That's the number of leaves in this tree. But the number of internal nodes in this tree is not more than the number of leaves. So that means the total number of nodes in the tree, leaves and internal nodes, is not more than 2 times n. And actually, the leaves, they don't even need to store arrays because there's nothing coming out of them. You could leave that out if you wanted. So only the internal nodes need to store this array of children. So now the size of this thing drops. Instead of sigma times big N, it's just sigma times little n. Number of strings in your set, not the total length of all the strings in your set. That's great. Searching, still the same amount of time. If I want to search for something, I look at the first character. That tells me which edge I have to cross next. In order to cross that edge, I compare the characters in my string to the characters that are on that edge. Either I get all the way across with everything matching, in which case I continue at the next node, or I realize before I get all the way across that this string is not in the set, so it doesn't make it across. And yeah, okay. So the cost of this search is still O of S. And now what about adding to one of these things? Well, that also becomes easy. So let's add chest. So I want to add the string chest to this Patricia tree. So I imagine I'm searching for it. I cross the edge whose label starts with a C, and I start matching my string to this thing, C, H, E. It's all good, except at this point, I have a problem. This has an E and my string has an S, which means that in my try, after I'm done inserting this, I can't have this edge with this long label on it. Instead, I need to split this edge into two. The top part is going to have the label CHE. The bottom part is going to have SE. And this node that I introduced is going to have another child, which is the rest of this string. Now, so that's easy, right? I mean, you follow the search path until you can't anymore. Typically, that will happen in the middle of an edge, in which case you split the node into the edge into two edges, and that newly inserted node will have a second child, which finishes the string that you're inserting. And okay, that all sounds good. How long does all of this take? Well, what are the operations we need to do? So we had an edge with this long label on it, and we needed to split it into two edges with these other labels. Well, these other labels, they're just substrings of the original label. So if these strings that label the edges, if they're labeled with P strings, this is a trivial operation to do. There's just one backing array back here, which contains the string cheese. And all of these labels here are just referencing parts of this array. So that split, I mean, the reason, sort of one of the reasons I needed to introduce P strings is you need to be able to do these splits in constant time, and P strings let you do that. And similarly, the label on this edge, the ST, well, it's just the suffix of this thing. And so we can put that label on there in constant time. Okay? So it doesn't matter how long the string is, the label on this edge or the rest of this string, once you've figured out where you need to put the new node, you create the new node. That requires creating an array. So that's going to take size of sigma time. And in addition to that, well, you had to first find the place where you needed to create that. That's the sort of slow part. You've got to search for your string, which takes time proportional to the length of the string. Right, so that's for the Patricia try. Does that make sense? Yeah. So in the array, so the array is just storing pointers to children. The array is indexed by characters. So the string you're looking for, you use its first character as an index into this array. And then, there's a parallel array or something which has the label of the edge that's coming out of this node, which is a P string. And that's the thing you use to traverse the edge. All right. So that's how you add. And here's something cool-ish. What about removing? So what's the issue about removing? And that should be easy. And indeed, it turns out to be, but there's a little subtlety here. So let's say I want to remove the string ape, A-P-E. So there it is. It's a leaf. So I should remove that leaf. But now I have a problem because I have a node here that has only one child. And everything I've been doing to argue that this structure isn't too big and whatever, that the internal nodes should have two children. So I need to get rid of this thing, which means I need to just make one edge here. One edge whose label is the first half of this one plus the second half of, or whatever, the first, I mean, whatever the label was up here and the label that was down here. Where am I going to get that label from? What's that? Yeah. So this label here, where did it come from? Well, I know where it came from. It came from the string apple, because that's where this ends. So this label here was a pointer to the P in apple and the second P in apple and the length of that thing. And this label up here, actually, I'm not sure. This label could have come from the string I just deleted, but I don't care about that. I know its length at least. And I know actually that the string I just deleted and the string that's left, they agree up until this point. And so to get this label, all I have to do is take this label, subtract, in this case, 1, but whatever the length of this thing was, add 1 to the length. So I'm just basically revealing the character that was always there to begin with. And I get the label that I need for this action. So that also takes constant time, even though it looks like you're merging two enormous labels potentially, but no, all you're doing is forgetting the upper one and remembering that the lower one actually contains the same thing. All right, so we have to stop there. It's a good place to stop, but let's let it sink in that this tree is really two things. There's this nice tree where everybody has at least two children, and there's labels on the edges, and those labels on the edges, you should think of them as being somehow separate. There's a place where all the strings are stored, and the labels on the edges are just pointing into those strings. So you can think separately about the size of the tree and the size of the stuff that's storing the labels off to the side. Because for P strings, the label is just two things. It's a pointer and a length. So you can think of the label as constant size, except it's stored somewhere else.
Sorry, Pat, I think I missed it, but how much does the remove take?
The remove takes as quickly as you can find it. So you search for it in O of S time.
Okay.
And then you have to, you get rid of a, you get rid of a node. You then check if the parent of that node has only one child. So that takes time that's the length of the alphabet. If you just look through the whole array to count how many pointers are not null. And then it takes constant time to do to fix the label. So that the remove takes the same time as add, searching for the string, plus in the case of remove, you have to look through one of these nodes to see if it has only one child or not, and which child it has. And that's it.
Okay, thank you.
Okay, so thank you. So look out for the second assignment, which will be posted within the next 24 hours. You'll have lots of time to do it, but since you don't have classes next week, you can use that time to look at that. Yeah, don't come to class next week. I'll see you in 2 weeks.